This video is going to be about rotational kinematics. We're going to focus on the relationship of rotational kinematics to the linear kinematic equations or SUVAT equations you've already learned so far. Let's start out by defining a few key terms. Angular position, which we'll represent with the Greek letter theta, is the angle swept out by a rotating body relative to a reference line. So if I have a body that's rotating around this circle with the axis in the center of the circle that starts at this point and moves to this point, this angle theta would be the angular position of my object. The next term we're going to use is angular velocity, or sometimes called angular speed, which we'll represent with the Greek letter omega. Angular velocity is the rate of change with time of the angular position. So if I go from this point to this point, I would change my angular position. The amount of time that it took would be my omega. So angular position, change in angular position divided by change in time is my angular velocity. The last term we need to define is angular acceleration, which we'll show with the Greek letter alpha. Angular acceleration is the rate of change with time of the angular velocity. So it's the change in omega, or angular velocity, over the change in time. That's equal to alpha, or angular acceleration. Now let's look at how the linear SUVAT equations compare to their rotational equation equivalents. So the equation displacement is equal to initial velocity times time plus 1/2 acceleration times time squared has a rotational equivalent, which says that angular displacement is equal to the initial angular displacement, which we'll show by putting a naught next to the theta, plus 1/2 alpha for angular acceleration times time squared. So we just basically substitute angular displacement for displacement and alpha for acceleration. Another SUVAT equation you learned was that the displacement is equal to 1/2 the initial velocity plus the final velocity times time. We can make the same rotational equivalent of that equation by saying the angular displacement is equal to 1/2 times the initial angular velocity plus the final angular velocity times the time. The third linear equation you learned was that final velocity is equal to initial velocity plus acceleration times time. We can write a similar equation where we use angular velocity is equal to final angular velocity is equal to initial angular velocity plus angular acceleration times time. And lastly, final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. That's equal to final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times angular displacement. So just a reminder, just like the SUVAT equations, which assume all acceleration is constant, the rotational kinematic equations all assume that the angular acceleration alpha is constant. That's the end of the video.